Now, in other words, from the thing we haven't proved but are willing to accept because we're lazy. I'm lazy. You guys are hardworking, but in other words, the one parameter subgroup which is generated by X fits in G. Those X are in the algebra. All right.
So what does it mean by the identity component exactly? Just
It's the connection component that has the identity in it.
Yeah.
just that it has identity in it? Okay.
So
I think-
ON, SON would be that connected component.
I think here, because we're not dealing with anything too pathological, because because Lie groups are groups with a manifold structure, all right? In a manifolds, in terms of topological spaces, manifolds are very boring. In a manifold, if I recall correctly, connected implies path connected.
That makes sense.
So I know it does make sense, right? But there are pathological examples in topology which distinguish the concepts of connectedness and path connectedness. There's
Yeah, I would not know.
Yeah, I mean the connectedness is stated in terms of sets, whereas path connected is what it sounds like. It's take 2 points. Is there a continuous path going from one point to the other?
Right, so I could see how the whole set wouldn't be connected.
Right. I mean, there's this. It's something. It's the topologist sine curve is a standard example of a set which is connected but not path connected. Anyway. I think it like basically forces the path to be discontinuous or something. I mean, all right. So anyway, so what look, it's very. I mean, so once you remember, once we have the definition back in mind, this is really easy to prove, right? So like, what's e to the? So if you look at let's say alpha of t, right, equal e to the tx. What do you got?
Alpha of 0 is I, alpha of 1 is e to the x. So it's path connected.
Okay. So there you go. There's I. There's e to the x. There's that path going from one to the other. So that shows you that e to the x is in fact in the same path component, or if you just like component, same connected component's identity. Proposition 2.17. If G is a matrix-like group, and with the algebra frac G, and if X is an element of the algebra, okay, and A is an element of the Lie group, then hey, uh-oh, what's that about? Oh no. Nothing bad. But some people I need to call on the phone, but like the process of calling them is hard. Okay. Really need to talk to them in person, it's just easier. All right. So in other words, conjugation by a group element, So look, I mean, this is where his definition of the algebra is just too stupidly easy. I'm sorry, but like, so, what? No, that wasn't the theorem. This, not equals X, but this is also in G. Sorry, I'm an idiot. Not that it's equal to G, but that's in G again. So all you have to do is to show that
Exponential.
e to the t times a inverse xa, right? But we proved for the matrix exponential that that's
Oh,
a inverse e to the t xa, right?
Right.
And
Which is just. Isn't that just like a diagonalized form of something that's in G?
let's see here.
Well, now it's a product of elements in G, so we're good.
Oh, right, which is again an element, exactly, this is an element of G, right? Since G is a group. So therefore, T was arbitrary. A inverse. I'm sorry.
Did we ever show that this definition of Lie algebra is the same one as the other one?
Well, I'm sure it will happen. It's probably about to happen. Okay. Now, I mean, he's about to. His next move is to show you that this Lie algebra has a vector space structure. Let's see how that goes. It's not at all obvious, right? It's not entirely obvious why this thing. This is actually a pretty nice example of an abstract vector space because it's defined in such a kind of wacky way. I mean, usually, as hard as I try to make an abstract vector space abstract, it boils down to just, it's some sort of Cartesian product or matrix of stuff you already know as vector spaces, and then you add them, so it's still additive. I mean, like, the trickiest thing I ever find in linear is like null spaces. Oh my goodness, null space is so sneaky. This on the other hand, this is actually a little bit intertwined. I mean, this is kind of a little bit sneaky. So the point here is basically that frac G forms a real vector space. Okay, so how is that? That's theorem 2.18. So theorem 2.18 says for G a matrix Lie group, all right, if you have x and y in frac G, and well, that's it. Okay, then number one, s times x is an element of frac G again for all s in the reals. So he's about to prove it is a real vector space. He's showing it's closed or scalar multiplication by a real number. This may be happening inside GLNC, but the vector space structure we're studying here is in fact out of a real vector space too. X plus y. It's an element of frac G.
It's 5 o'clock
Shush!
p.m.
Silence! 3. And this is where the more abstract Lie algebra gets started here. xy minus yx is an element of G. So that has not so much to do with the vector space structure, but property 3 fact shows that G is a Lie algebra in the abstract sense, which is defined in a future section. Oh man. Well, the stuff that I'm about to get to will go much faster. I'm sorry, I seem to have wasted all our time on the log today. I guess that was necessary to appreciate what's going into that e to the tx thing. Sorry guys, I wanted to get further. I mean, we're not done yet, but even so, you can see the handwriting on the wall. All right. So what happens here? We look at what? E to the t, right? Times sx. What do you get then? This is nothing more than what? E to the like lambda x, right? Where lambda is some real number. And since x is in the Lie algebra of G, this is an element of G, right? Lambda equals to st. So therefore, s times x is an element of frac G as well, right? This is so these are stupid. T times what? X plus y. Oh. Huh. That seems like a thing.
So we can just... Can we use distributive property here? We allowed to do that?
Well, that's the thing. I mean, yeah, I can. I mean, absolutely. I mean, if you mean this,
E to the x plus e to ty. I mean, times e to ty.
but that's not true.
It's not.
No, and not unless x and y commute.
Why do they have to commute that the way? Oh, because then multiplication commutes. I see.
Right. There's something sneaky here. Oh.
Well, it's still...
Yeah, point 1 is immediate. Point 2 is easy to verify if x and y commute, since in that case,
Yeah.
yeah. If x and y do not commute, this argument does not work. You don't say.
Well.
However, the Lie product formula states...
Skip that.
Ooh, yes, I see. So yes, here, we'll make ourselves feel better. So this is e to the tx, e to the ty, which is again a product of element of G, which is once more an element of G, as G is a group, if xy is equal to yx. All right, but that's a very special argument. It's not usually the case going to work.
And we... Yeah, never mind.
Yeah, so what he says though is we got this formula that we could prove if we had more than 1 hour to work with here, but we don't, so oh well. Unless you guys want to meet more. E to the t times x plus y, not that I have time. The limit, sorry about that. If I could, if I could find a way to clone myself. Let's see here, all right. This is the Lie product formula. E to the t x plus y is equal to, all right, the limit is m goes to infinity of e to the t x over m times e to the t y over m, all to the m power. Very sneaky. Now,
What?
so like as n goes to infinity,
Isn't that an indeterminate form? No.
I mean, I would
Is it not?
I would suppose it is, but I mean, it's a kind of interesting thing. It's like these don't commute, right? But if you make them very, very small, whatever they're not commuting by. It's like the Baker-Campbell-Hausdorff formula, right? Eventually, we'll learn. If I ever figure out how to not waste time in here. Eventually, someday, I'll figure it out. But this is the formula. Right? Now this is AB minus BA, right? So like intuitively speaking, here's my understanding of this formula. It's these extra, and beyond that, there's an infinite series of nested commutators up there. This is the Baker-Campbell-Hausdorff formula. So if you think about doing something like this, right? These are pretty tiny, right? I mean, they're relatively tiny, and you know what? So are A and B, because it's like this plus this. It's still kind of tiny. But these guys, tinier still, because they're multiplying. That's like 1 over m squared. And the next term up will be like 1 over m cubed, 1 over m to the 4th, 1 over m to the 5th. And the limit as m goes to 0. Oh, phew. I was like, as m goes to 0, those are even more dominant. Oh, m's going to infinity. Okay, phew.
Yeah.
Okay, I feel better. So as m goes to infinity, those higher terms in the Baker-Campbell-Hausdorff don't matter, and it just leaves you with these. But then, to be fair, you started with x and y, right? Well, you could say you started with tx and ty. So you have to take that to the nth power to undo that. And so
Okay.
that's an intuition for why this formula might be working. I mean, but not proof. The proof is in this book. Which, by the way, is the algebras, the groups, the algebras, and representations, and elementary introduction. I should emphasize the elementary. All right, so where were we? Once you have this, let's see. That's in the group. That's in the group. The product's in the group. The nth power of the product is in the group, right? So you got a sequence. And where does it have to converge to?
Either the group or non-invertible matrices.
Right, but that's not possible because it's invertible, because it's the exponential of something, so it must converge to something in the group.
By the fact that it's a matrix Lie group.
That's exponential.
Yeah, by the fact that it's a matrix exponential, and then the fact that it has to converge within the Lie group follows from the fact that it's a matrix Lie group. Yeah. So we have a convergent sequence by this identity, right? I mean, it's this equals to that, so it's convergent. So consequently, this is an element of G, which then shows that T was arbitrary, so x plus y is an element of frac G. On second thought, I don't think I can use this as an example in linear. Not without a lot of...
Just say that x and y commute.
I would have to give... Oh. Yeah. It's not bad. That's not bad. I think a homework problem was just born.
Oh no. That'll have video evidence.
It will be called...
At least my face has never been on the video.
Correct.
Yeah, my face has never been on the video.
It will be...
147.
The Hoogerwerf...
You should do Neji Hoogerwerf again.
To what?
One of the problems in advanced calc.
You
The
name
ninja's name was Neji Hoogerwerf.
Neji Hoogerwerf.
Yeah, it was.
I should.
It was about his Byakugan.
I should do that.
I
I should say. Neji Hoogerwerf came to me in a dream and brought me this problem, told me this problem.
Yes.
I woke with a nervous sweat. Wrote it in blood. Or something, I don't know.
It was written in shuriken on the wall.
Yes. So the definite, and then of course the last thing is to show that this is in the Lie algebra, right? So how's he do that? Well, ooh.
Is this one even worse?
Oh, actually, this is really cool. This is really neat. Here's the one that actually involves some kind of sneaky calculus, basically. So what he does is he looks at... I'm going to jump right to it. ddt of e to the tx. Now look at this, e to the txy, right? E to the txy, e to the minus tx, right? So what's going on here, this both in the group, it's like the a over there, right?
Yeah.
And so y in the Lie algebra, so this is once more in the, you know,
Wait.
Yeah.
right in Lie algebra. That's kind of neat. I don't know what that does for me.
But how do we?
Derivative.
But what do we start with? Don't we start with like e to the t times xy minus yx? How do we get to that from the definition of the algebra?
Oh, well, I mean, let's see here. So his point is if you differentiate this, right? By the product rule, you have on the one hand, how's it go here? Well, he plugs in t equal to 0, so the exponentials go away, and what you have is xy minus yx. Do you guys see why that is? So derivative of this one pulls out an x, derivative of that one pulls out a minus x. When you plug in time to 0, the exponentials drop out, and you're just left with that. Does that make sense?
And so, okay, so you differentiated something that was in the group and got it that, which means that that's in the group.
Okay. Now, what this shows, all this shows at the moment, how can I say this? So this, I'm not sure what this means. Well, wait a minute. This is what? This is isn't this in the Lie algebra not just for one time but for all time?
Yeah.
Yeah, so that's actually a curve in the Lie algebra
You mean for all, like,
for all t. Because I mean
Seems
basically,
like it.
I mean a is equal to t e to the tx. I can do that for arbitrary t.
yeah.
So what's his argument here? He goes, so he says by proposition 2.17, that one, this is e to the tx y, e to the minus tx is an element of G for all t
Oh my gosh.
in the reals, right? Furthermore, we have by points 1 and 2 established that G is a real subspace, right? So that means that G is a topologically closed subset of M and C, and it follows what? He says it follows that. Do you guys understand that?
This one, two, zero space.
Let's see how we get the difference quotient from.
So that's the definition of the derivative, right?
Right.
So,
So if you have a curve on a closed subspace, right?
yeah.
The question is, why does the derivative of the curve have to also be on that subspace? I think, isn't that what he's arguing? I mean,
Seems like it. He said it's topologically closed. I don't know if that.
I mean, this is nothing more than the explicit limiting process that's in. I mean, this is just another way of expressing that derivative in terms of a limiting process.
Right. So, I kind of feel like saying it's closed, so the limit's going to be in an element of it. But
Mhm.
like, this isn't really a sequence. It's like, before we were looking at limits of sequences, this isn't it.
Oh,
Not really a sequence.
I mean, I suppose you could.
So you could try to turn it into.
You could, I guess you could I mean, if that's one way you want to look at it, you could do that. I suppose you could say, if that limit exists, then so does, by the exchange between, continuous and sequential limits. I could take a sequence converging to 0. But it has something to do with the fact that this is happening inside a vector space too, right? Like, I mean, if you can just think about this for a second. You're inside a vector space, right? And you're taking the derivative of a curve inside a vector space. There's no way you could get off the vector space under differentiation. But he's using this closed argument too, though. I don't think this is not something that is impossible to understand. I just don't have. I haven't picked the easiest, lowest. I mean, it's once it comes to us, it's not going to be a big deal.
I mean, he's looking at arbitrarily small portions of the curve in a closed subspace, right?
Yeah. What does it mean for the Lie algebra to be closed in what sense? That means, you said in terms of sequential.
He said topologically closed.
Yes, topologically closed. So what does that tell us about?
Didn't we have the thing where, if it converges to something inside the set, or it doesn't converge at all, or?
Yeah, remember if you have a sequence, how's it go? In a closed set, if you have a sequence that converges, it has to converge to a element of the set.
Yeah.
So the same is true for these kinds of limits. Yeah.
But why can we say that the same is true of these kinds of limits? I'm not sure why.
Right. Well, we know that we are adding and subtracting things inside a vector space, right?
Mm-hmm.
But the thing we're taking a limit of is inside the vector space. I'll let you guys think about it. We gotta go, but I'm sorry. I don't think this is anything too. I don't think it's anything too hard. I think once you guys understand it, you're like, no. I mean, yeah. Shut up.
So maybe Neji Hugoworth will come to me.
Yeah, maybe Neji Hugoworth will tell me in a dream.